Welcome, ladies and gentlemen. Let's go ahead and solve these systems. Based on what the original system looks like, we'll select and use a different method. So what I'm going to do is ask what method you used to solve that first system in number 1. So what method did you use to solve that first system? Nathan? Elimination. Raise your hand if you use the same method as Nathan. Elimination? Me too. So it looks like we were already lined up and we had exact opposites in the y variable, and so we're all set for the third step, which is to add the equations together. So we're all set up for elimination, and that's the most efficient way. So we'll go ahead and do top to bottom. 7x plus 2x, I get 9x. Negative y plus y equals 0, and the y's are eliminated. Yay, bring down the equal sign, negative 3 plus negative 6 is negative 9. So it looks like we can finish this out through division. I'll get x equals negative 1, and I'll go back into either of my originals. So it looks like that smaller, let's see, that bottom one has a positive coefficient on the y term, so I think I'll use the second equation. Does it matter? No, you could have used the first equation, right? Either equation is going to work. We know that our solution of the system is going to satisfy both equations in my system, so you can select whichever one you want. I'm going to do the first one, or the second one rather. So 2 times x plus y equals negative 6, and it looks like x was negative 1. So negative 2 plus y equals negative 6. And I can finish it out through addition. It looks like y equals negative 4. So my potential solution point is negative 1 comma negative 4. But before I box it, just like on your quiz next class, I strongly encourage you to check that ordered pair x comma y in your original system. It must satisfy each equation in that system in order to be a solution. So let's go ahead and check quick. 7 times negative 1 is negative 7. Minus negative 4 is plus 4. Does negative 7 plus 4 equal question mark negative 3? Yes, it does. And negative 1 times 2 is negative 2 plus a negative 4. Negative 2 plus a negative 4 is negative 6, and so it looks like that satisfies each of them. Raise your hand if you had negative 1 comma negative 4 already. Negative 1 comma negative 4. Yes, good job, you guys. Let's take a look at the second one. What method would you like to use to solve the second one? So what method would you like to use to solve that second one? Ian? Substitution, I'm down. It looks like that first equation is already solved for one of the variables. And so I'll go ahead and use substitution method because y is already by itself. And so I'll rewrite that second equation, except everywhere I see a y, I'm going to go ahead and substitute in that expression, negative 1/4 x plus 6. So let's go ahead and rewrite that. 4 times y plus x equals 48. And then in for y goes negative 1/4 x plus 6. So we'll go ahead and distribute. Watch your signs, guys. I get 4 times the negative 1/4 x is negative x plus 24 plus x equals 48. I combine my terms, same side, same operation, and I get negative x plus x combines to 0, and I get 24 equals 48. When I see this, I immediately go, what is going on here? Huh? Interrogating? That was a happy face there. That was close. You guys see that? That was close. And I don't want a happy face. I want a, huh? What's going on? Right? And so I've generated algebraically an equation that's sometimes true, always true, or never true. Right? Is that equation sometimes true, always true, or never true? Joe? Never true, and so that's an indication that I have how many solutions? Mark?
0.
Yeah, 0 solutions. And so when I get this statement, right, when I get this statement, 24 equals 48, that's an equation that's never true. That's my algebraic indication that I must be dealing with a system that has no solution. And so I'm going to go ahead and write that for my answer, and that's all about. This would be no solution. Raise your hand if you determine there are no solutions to number 2. Way to go, you guys, and we're one to go. Number 3, it looks to me like this is all set up for substitution as well, so I'm going to go ahead and put an asterisk next to that second equation. I'll rewrite my first equation. 5 times y equals 10x plus 20. In for y, I'm going to put 2x plus 4. Because that's what y equals. Distributing, I produce 10x plus 20. Equals 10x plus 20. And by golly, if I were to add or subtract, get all the x's on one side, and everything else on the other, I would get 0 equals 0. And again, I'm running into a special situation, right? What's going on here? So is this equation sometimes true, always true, or never true? Hannah? This is always true, right? 0 equals 0. Or the one above it, 10x plus 20, is always equal to 10x plus 20 no matter what x value I choose. And so this is an always true equation. That means that we're dealing with a system that has how many solutions? How many solutions would this system have? Rachel?
Infinite.
Yeah, infinitely many. Any point on that first line is going to also be on that second line. So this is a situation where we have infinitely many solutions, and that's what we're going to box. So infinitely many solutions. Awesome. Uh-oh. I want infinitely many solutions. Can I fix that? Maybe. Close the snap. Ooh, look at that. It'll work out. Infinitely many solutions. I went from the ugliest box I'd ever created in class in my life to the second ugliest box I'd ever created in class in my life in one zero feature. So that's pretty sweet. All right, so let's go ahead and sum it up. We had -1, -4. What was the first solution? -1, -4. We had no solutions. Number 3, we had infinitely many solutions. Go ahead and decide right now with your partner which of these systems are consistent, which of them are inconsistent, and I'm going to call on you to share with the whole class. So which are consistent, which are inconsistent?
The first and third one are.
Okay, number 1, consistent or inconsistent? Samantha and Casey? Consistent. Raise your hand if you had consistent for the first one. Consistent because all we need is 1 or more solutions. Good. So consistent for the first one. Uh-oh. Consistent or inconsistent for our second one? Jacob and Emily? Inconsistent. Raise your hand if you had inconsistent for number 2. No solutions. Inconsistent. Good job. Inconsistent. Inconsistent. And lastly, infinitely many solutions. Is that consistent or inconsistent? Aaron and Will?
Consistent.
Consistent. Good job. It just takes 1 solution to be consistent. If we have infinitely many, then we have more than 1. So that's definitely consistent. Awesome work, you guys. What questions do you have on today's Bellwork discussion? Okay. Then let's go ahead and pause the recording and we'll take care of our homework check. All right, what are the dimensions of the following matrix? Dimensions of the following matrix, don't call out, be ready, I'm going to call on you. What are the dimensions of that matrix? Keeping in mind how we name, right, our dimensions. Jock?
3 by 5.
3 by 5, raise your hand if you had the same as Jock. 3 by 5, that's right. We need to know because the number of rows versus the number of columns is going to make a difference if we try to perform operations. And such will be the case when we solve using matrix equations, all right? What is the row 2, column 4 entry? Get ready. Row 2, column 4. Andrew?
34.
34, awesome. There's our row 2, column 4, good. I'm going to write down those dimensions too, 3 by 5. And lastly, what row column is the element 1? What row comma column is the element 1? Carson?
Row 3, column 4.
Row 3, column 4, awesome. So, row 3, column 4, nice job. So we've got our dimensions of a matrix, right? We know how to name them in terms of their dimensions, and we know how to find corresponding elements. Great. So now what we're going to do is we're going to take a look at solving a larger system that is more than 2 equations, 2 variables. In this case, it looks like we have 1, 2, 3 variable system, x, y, z, and 1, 2, 3, 3 equations. So this is what we call a 3 by 3 system. We've got 3 variables and we've got 3 equations. What we're going to do is first solve this using the algebraic methods we already have. And so we're going to solve this algebraically using the methods we've already developed. The idea here is that we can chunk this down from a 3 by 3 system into a 2 equation, 2 variable system, a 2 by 2 system like you guys already solved for Bellwork, and then we can handle it using regular substitution or elimination method. In order to do that, however, we need to get rid of one of those variables, right, in 2 different ways. And so first thing I need to do is scan my system, and I want to look for the first one that could add to 0 immediately, right, getting rid of one of the variables, or that will create the simplest multiplication. And so again, I'm trying to get rid of the same variable in 2 different ways. As I scan the problem right now, it's already set up to get rid of one of my variables. Can you find it? Right? One of those variables could already be eliminated if I chose purposely, right, to use 2 of those equations. Everybody see it? So what could I get rid of right away? Rachel? We could get rid of z, right? Which equations would I have to combine right now through addition in order to get rid of z's? Rachel?
You can do 4z minus 2z, and then multiply the second one by -1 times 2z again.
Oh, yes. Let's label our equations. So this will be a lot easier. So let's go ahead and when we have 3 equations, 3 variables, I'm going to go ahead and label my equations. This is equation 1, equation 2, and equation 3. Okay. I agree with Rachel that z's are going to be the easiest to get rid of. If you guys take a look at the system, are there already exact opposites in my z's in 2 of the equations? Yeah, right? I already have exact opposites in equation 2 and equation 3. In equation 2, my z term is positive 2z. In equation 3, my z term is negative 2z. Those are already exact opposites. And so what I'm going to do to eliminate the z's is to add equations 2 and 3 together as is. And so let's go ahead and rewrite equation 2. Bless you. Equation 3, and we'll add those together. So equation 2 as is was 3x minus 3y plus 2z equals 27. Equation 3 as is 4x plus 5y minus 2z equals 4. Because I have exact opposites in one of the variables, I can now add them together and eliminate that variable. So let's go ahead and add equation 2 plus equation 3. I get a new equation. That equation is 3x plus 4x is 7x. Bless you. Negative 3y plus 5y is plus 2y. 2z minus 2z is 0. We've eliminated the z's. Bring down the equal sign. 27 plus 4 is 31. So we've created a new equation. I'm going to call this equation 4. Equation 4 is different than the originals because it just has x's and y's. Now let's get rid of z's, right, using a different pair of equations. If I can get rid of the same variable a different way, then I'll have 2 equations that each contain x and y, and it'll be like a Bellwork question. So let's go ahead and scan my original 1, 2, and 3. Let's come up with a strategy that will eliminate z's in a different way, using 2 different equations. I can't use 2 and 3. Right? I've already used up 2 and 3. Let's get rid of z a different way. All right, so does anybody have a strategy for getting rid of the same variable but a different way? Blake?
You can do 1 and 3 and then multiply 3 by 2.
We could do equation 3 by 2 and then use 1 and 3 to eliminate z's again a different way. Absolutely, that's a great idea. So let's go ahead and do 2 times equation 3. So we'll do 2 times equation 3. So we'll do 2 times equation 3, and when we do that, we get 8x plus 10y minus 4z equals 8. Do we do that every term by 2? Everybody see that? Now let's go ahead and combine that with equation 1. as is. Equation 1 was 2x plus y plus 4z equals 20. In Blake's strategy, we've created exact opposites in the z terms again. It needs to be the same variable, but we've done so using a different pairing of equations. So let's go ahead and eliminate those z terms by adding, again, top to bottom. Here we go. 8x plus 2x is 10x. 10y plus y is plus 11y. Negative 4z plus 4z is 0. We've eliminated the z's again, and 8 plus 20 is 28. In this way, we've created a new system. We'll call this equation 5. By getting rid of the z's using a different pairing, in this case we used equation 1 and 3, and we created a new equation. That equation, check it out. Just has x's and y's in it, like our Bellwork. Our number 4 equation just has x's and y in it. Now we can solve this new system of 2 equations, 2 variables, using traditional means. So I want you to go ahead and scan those and come up with a way that we're going to solve this system. I'm going to go ahead and copy this to the next page. All right, so what should be our strategy then for solving this 2-variable, 2-equation system? What do you want to do here? Does substitution look like the way to go? Hans? No, how come?
Because there isn't anything that states what variables.
Absolutely, right. It would be hard to get y equals or x equals, right, alone. All my variables have coefficients of 1. But they're all lined up. And so what should be our strategy to get our opposites? Right, what can we do to get opposites here? Andrew?
Multiply number 5 by 2 and then number 4 by negative 11.
Absolutely. We could multiply that equation number 5 by 2 and then equation number 4 by negative 11. That would create exact opposites in which term?
The y.
In the y's, right? So if we want to get rid of the y's, we can certainly do that. So let's go ahead and do that. 11, I'm wondering if 10 is going to be better than that or not. Oh, no, I'm down. I like your strategy. So let's go ahead and multiply the top one. You said by negative 11. And rewrite. So here we go. Negative 11 times 7 is negative 77x. Plus 2 times negative 11 is minus 22y equals, and then 3 times, I'm going to make it go smaller. Group it. Group it. And then 11 times 3 is 341. 341? Can somebody do a quick check on a calculator with that and see?
Yeah.
341? Awesome. I just did 11 tricks, split them, and then add the 2 to just to get the middle. Aaron?
It should be negative.
Ooh, negative. Thank you very much. Good catch. Thank you, Aaron. I appreciate that. So negative 341. All right. Andrew's strategy was to multiply the second equation all the way through by 2. So let's go ahead and do that and see what we get. So 2 times 10, 20x, plus 2 times 11 is plus 22y. Ah, the fruits of our labor, I see. We are going to eliminate the y's here in just a minute. Equals 2 times 28 is 56. All right, guys, let's go ahead and do it then. Here we go, top to bottom. Negative 77x plus 20x, negative 57x. Negative 22y plus 22y is 0. That's what we did. We eliminated the y's by creating exact opposites. Negative 341 plus 56 looks like 285.
Negative 285.
Negative 285. Goodness. Looking bleak. So it looks like 57 hopefully goes into negative 285, but it might not. right? We could see by doing, let's see, 60 would go 4, 5, 5 is 35. Nope.
Yeah.
5 times exactly?
Yeah.
Awesome. That's really nice. Well, little words there for a moment. We have to work with the F word. Fractions, right? Get that on the recording. Okay. So I got x equals 5. Now where can I go to get what y equals? Well, given that x equals 5, I can now go to one of my 2 by 2, right? My x and y equations. So I'm going to go ahead and go into equation 4. So I'm going to plug this now into equation 4. So when I plug this into equation 4 and rewrite, I'll get 7 times x plus 2y equals 31. Except n for x is going to go 5, what we just found. So 35 plus 2y equals 31. Subtraction isolates the y term and gets 2y equals negative 4. Division solves for y, and I get y equals negative 2. Goodness gracious. So at this stage in our lives, we've got an x value. We've got a y value. Where, pray tell me, could we go and find out a z value? Well, it's not going to be in equation 4. It's not going to be in equation 5, but it could be in any of the originals. And so again, I'm going to go ahead and purposely choose one of the original equations. X is 5, y is negative 2. I think I'll go ahead and substitute. I'll substitute into maybe that first one. I'll go into the first one. So I'm going to go ahead and plug this now into equation 1. Here we go. We're going to write equation 1, except everywhere we see an x, we're going to put 5. Everywhere we see a y, we're going to put negative 2. And then we're going to solve for z. So I need to switch this over somehow. All right, let's do it. In for x goes 5. In for y goes negative 2. 2 times 5 is 10. Plus a negative 2 is minus 2. Plus 4z equals 20. Combine like terms, same side, same operation. 8 plus 4z equals 20. Subtract 4z equals 12. Divide and z equals 3. By golly, we've generated an x value, a y value, and a z value. Could it be that my answer, right, is no longer a point x comma y, but now a point x comma y comma z? Yes, that's right, an ordered triple that represents the solution to the system. And so what I'm going to do is write my potential solution point x comma y comma z, just like we write an ordered pair, but now an ordered triple. This is a 3 equation, 3 variable system. So I'm going to write my potential solution point as 5, negative 2, 3. However, before I box it, you guessed it, I'm going to check in the original. So here we go. 2 times 5 is 10. Minus 2 is 8. Plus 12, does 8 plus 12 equal 20? Yes. X into the second one. 3 times 5 is 15. Minus 3 times minus 2 is plus 6, is 21. 21 plus 2 times 3 is 6. Does 21 plus 6 equal 27? Yes. And lastly, 4 times 5 is 20. Minus 10 is 10. Minus 6 is 4. And so it satisfies all 3. I'm confident in my answer. Wow. Take a break. Shake it out. Shake it out. So what's different when solving a 3-variable, 3-equation system? Well, we've got one more layer. We must first chunk it down to a 2 by 2 system by eliminating the same variable in 2 different ways. Such is going to be the task for you and your partner in this next system. We're going to go ahead and give you a chance to try now solving this 3-equation, 3-variable system. And we're going to go ahead and give you 4 minutes, and I'm going to pause the recording as we go through, and I'll go ahead and start now. You can come up with the strategy, and then we'll share our response on the whiteboard. Same answer. Okay, so what variable did you and your partner decide to get rid of? Caitlin and Megan? Oh, what did you choose to get rid of in order to, because I saw that you solved for z first, but you got rid of which variable? Y, awesome. And so it looks to me like we can already have exact opposites in the y variable, right, in two different equation pairings. It looks to me like 1 plus 3, or 1 plus 2 first I'll do. 1 plus 2 first would get rid of the y's because it's plus y and minus y are exact opposites. So everybody, let's do 1 plus 2, and I get 6x plus 0 plus 16z equals 12. So I've got a new equation, and I'll call this equation number 4. Next, I'll use a different pair of equations to get rid of the same variable. I'm going to get rid of y's again. I have to get rid of y's again if I've gotten rid of y's in the first place. And so now I'll go ahead and do equation 2 plus equation 3. Equation 2 plus equation 3 will create a new equation. That equation is x plus 5x is 6x, minus y plus y is 0, plus 10z minus 2z is plus 8z, equals 9 plus a negative 9 is 0. This is my new equation, and I'll call it equation 5. All right, so I've generated a two variable system. Now it's like Bellwork. The only difference is instead of having x's and y's, I've got x's and z's. But it's still two equations, two variables. I have enough information to solve. So what strategy would we like to do now? How about 4 minus 5? Do you guys see that? If we multiply this bottom one through by a negative 1? If I did a negative 1 here and rewrite that, wouldn't I get negative 6x minus 8z equals 0? When combining that with plus equation 4, equation 4 rewritten as 6x plus 16z equals 12 would create exact opposites in the x's. And so now I'll go ahead and add these together, and I'll get 0 x's plus 8z equals 12. Finish it out through division, and I get z equals 12/8, which is the same as 3 halves. Raise your hand if you had 3 halves for your z variable. Your 3 halves for your z variable? Way to go, you guys. I can now go back to either of my two variables equations, right, that has a z in it in order to figure out what x is. And so I'll purposely choose this red equation number 5. So I'm going to plug this into number 5. And when I do that, I get 6x plus 8z equals 0. But z we just found to be 3 halves. So I get 6x plus 8 over 2 is 4 times 3 is 12 equals 0. So 6x equals negative 12. So x equals negative 2. By golly, we so far have x equals negative 2. We've got z equals 3 halves. I'm going to go ahead and import that to this next page. No. I don't know what I did. Now it's not going to work unless I use the mouse. So I'm going to import that from the last page. Oh, it's working. So from the last page I had x equals negative 2 and z equals 3 halves. So we can take our pick, whichever equation we want. I'm going to pick one that has a positive y value. So I'm going to now plug these into equation 3. and rewrite 5x plus y minus 2z equals negative 9, except x equals negative 2 and z equals 3/2. Let's solve for y. 5 times negative 2 is negative 10 plus y minus 2 times 3/2 is 3 equals negative 9. Combine like terms, same side, same operation, negative 13 plus y equals negative 9. Opposite side, opposite operation. I'm going to add over. I'm going to add over that 13 and I get y equals positive 4. Oh my goodness. So what ordered triple am I going to check? Go ahead and tell the class when I call on you. So what ordered triple am I going to check? Mark?
Would it be negative 2, 4, 1.5?
Yeah, let's go ahead and check negative 2, 4, 1.5 in my original. So here we go. Negative 2, 4, 3/2. I'm going to check that in my original before boxing. So here we go. Negative 10 plus 4 is negative 6 plus 9 is 3. Negative 2 minus 4 is negative 6 plus 15 is 9. Negative 10 plus 4 is negative 6 again, minus 3 is negative 9. By golly, we found our winner right here. And so that's pretty sweet. Okay. So we solved two, right, different systems that included more than our two variables x and y that we're used to. We solved a three variable system. And while these worked out pretty well, it did take significantly more work than our Bellwork questions. What we're going to do today is solve using matrix equations. And this is going to be a much quicker, more efficient method, so long as we're allowed the use of graphing calculator technology. So let's go ahead and take a look at our solving linear systems using matrices and the calculator. The basic premise of solving a system with a matrix equation is similar to solving regular equations. We're going to use not inverse operations, but inverse matrices and our matrix editor in our graphing calculator. And so, just like we have solved the equation 2x equals 5, where 2 is my coefficient, x is my variable, and 5 is set equal to a constant. So too do we have similar terms for a matrix equation. A is just a matrix, it's the coefficient matrix. X is what we call the variable matrix, and then that's set equal to a constant matrix. So everybody look at my little baby equation I made up, 2x equals 5. What do you do procedurally to solve this equation? Right? What do you do procedurally to solve this equation? Jacob? You divide by 2. Division is the inverse operation for multiplication. Right now this is 2 times x. We're going to do the inverse operation in order to solve. It's just with matrices that looks a little bit different. And so with matrices, we're going to go ahead and multiply both sides by A inverse. That's the inverse of matrix A. When I multiply A inverse times A, it gets rid of that matrix, that coefficient matrix, and leaves me with that variable matrix alone, which is what we want to do when we solve an equation, is get the variable alone. When we solve a matrix equation, we want to get the variable matrix alone. And so basically on our home screen, after editing my matrix features A and B and X, I'm going to go ahead and solve by putting A inverse times B on my home screen. This is what we're going to be entering to solve. So this is the key. We're going to multiply both sides of my matrix equation by A inverse. What that'll look like procedurally for us is simply multiplying A inverse times matrix B, and that'll give me my answer, my variable matrix X. This is going to be super, super cool and efficient. Let's go ahead and see if we can't work this out then using a graphing calculator. So let's go ahead and take a look at this system. In order to generate our coefficient matrix in our graphing calculator, what we need to do is take my original three variable system, and create a coefficient matrix. The coefficient matrix is named because it's gained by grabbing the coefficients on each of my variables in order and each of my equations top to bottom. So let's go ahead and write this new coefficient matrix in blue. My coefficient matrix is the number of equations, 1, 2, 3, by the number of variables, 1, 2, 3. It's gained by grabbing the coefficients from x, y, and z in order respectively. Let's go ahead and write that blue coefficient matrix. First equation, the x coefficient is 1. Y coefficient, 1. Z coefficient, -1. That's the first row in my coefficient matrix. Second row, x coefficient is 3. Y coefficient, 2. Z coefficient, 4. That's the second row of my coefficient matrix. What do you think the last row of my coefficient matrix is going to be? Kenzie?
-1, 5, and 1.
Absolutely. Everybody go ahead and complete your coefficient matrix. My variable matrix is a little bit different. My variable matrix is the variables, just like you wrote your points in that point matrix last class. You did x on top and y on bottom. We write our point matrix here. It's just that it's not going to be x and y. It's going to be, you guessed it, x, y, z, because this was a three equation system. My ordered triple would be the answer, x, y, z. I need an x, y, z as an answer, and so my point matrix is x, y, z. That's my variable matrix. Equals, and then my constant matrix. My constant matrix is gained by taking the constants in order from top to bottom. My constants are 4, 17, and 8. Take a minute and make sure you've translated our given three variable system into a matrix equation. So that's coefficient matrix times variable matrix equals constant matrix. Does everybody see it? What are we going to do to solve this? We're going to multiply both sides by A inverse. But to get that, we're going to use our graphing calculator. So everybody to the graphers. On our graphing calculator, we're going to edit a new matrix A, which is what dimensions? It's my coefficient matrix. 1, 2, 3 rows by 1, 2, 3 columns. So everybody, where's that matrix editor? Remember, it's row 4, column 1. Second inverse is the matrix editor. And so in my matrix editor, I want to edit matrix A. Matrix A, however, I want to be what dimensions? 3 by 3. And so I have to change it to 3 by 3. And I'll do my coefficients in order from left to right. So 1, 1, -1. Everybody make your matrix A. 3, 2, 4. -1, 5, 1. Take a minute and make sure you have the correct sign. If you have one mistake with typo, it's going to mess up your whole problem. So I'm checking. 1, 1, -1. 3, 2, 4. -1, 5, 1. Awesome. Because we're entering on our home screen, we're aiming towards entering the circled asterisk A inverse times B. We need just matrix B now. And so let's go ahead and do matrix B. So I'll go to my matrix editor, and this time I want to edit matrix B. Right? So now I'm going to edit matrix B. Matrix B, I want to be what dimensions? Not 2 by 3, but what? 3 by 1. So everybody, let's set our new matrix B dimensions up as 3 by 1. Top to bottom, 4, 17, 8. So we've created a new matrix called matrix B. That's our constant matrix, 4, 17, 8. Here comes the big finale. On my home screen, I'm trying to enter A inverse times B. Procedurally, what's going on is we're multiplying both sides on the left by A inverse. And A inverse undoes that coefficient matrix A to get my variable matrix, my point matrix, x, y, z alone, so I can see what my values of x, y, and z are. Procedurally on the calculator, it's as easy as pulling up A inverse and then multiplying it by B. So let's do that on our home screen. Ready? Now that we've got our matrices edited, we'll go just to our home screen. We're going to pull up the matrix named A, so we'll go second matrix. We want the matrix named A. We want to now press the inverse button, that same matrix editor button that was the -1, that x to the -1, we now push to create the -1 on my A. That's saying take the inverse of matrix A. Does everybody see that? Times matrix B, right? We're trying to multiply it by matrix B. So now times matrix B. Where's matrix B? That's in my matrix editor, so I pull up the matrix named B. Again, second inverse is matrix, toggle down to B, names B, and on my home screen I now have A inverse times B. Check and make sure you have that. Everybody good? If you don't, ask your partner how to get it. And the moment of truth. Voila! The calculator spits out an ordered triple XYZ that's equivalent to my variable matrix. So guys, it looks to me like A inverse times B is equivalent to 3, 2, 1, which means my ordered triple must be, you guessed it, 3, 2, 1. A quick check in the original. 3 plus 2 is 5, minus 1 is 4. 3 times 3 is 9, plus 4 is 13, plus 4 is 17. And -3 plus 10 is 7, plus 1 is 8. By golly, we've generated my ordered triple. While my matrix spits out, right, x, y, z as a point matrix, a variable matrix, we're still going to write our answer to a system as an ordered triple, just like we did for Bellwork. Does that make sense? Or our 3-variable, 3-equation system. How slick is that? Let's go ahead and verify our findings algebraically then from before, now using our matrix editor feature. So everybody, let's go ahead and do a new matrix. Let's write a coefficient matrix times variable matrix equals constant matrix. And so we'll go ahead and do our coefficient matrix A times our variable matrix B, I'm sorry, X equals our constant matrix B. In our graphing calculators, we'll enter a new matrix. Our coefficient matrix, then in blue, would be 2, 1, 4, 3, -3, 2, 4, 5, -2. Our variable matrix from top to bottom would be X, Y, Z. Our constant matrix, in order, top to bottom, would be 20, 27, 4. All right, guys, let's do it. So in my graphing calculator, we'll go ahead and make a new matrix A. So I'm going to do second matrix, and I'm going to edit A. I still want 3 by 3, but now I want new coefficient matrix 2. Oops. 2. One, 4, 3, -3, 2. Everybody do it? Make sure you have the correct coordinates, otherwise, or coefficients rather, otherwise it's going to mess everything up. My matrix B, second matrix, edit. B, still 3 by 1, but now my entries are 20, 27, 4, and home screen. Second, A inverse. So I want the matrix named A inverse. I gotta orient this thing before I go insane. Times matrix B. Gosh, I hope it's integers. Hey! It's such a dull feeling, a leaden feeling in your stomach when you do all that, and then you get 0.73 and 600, and you're like, oh. Love it. 5, -2, -3. What did we get when we did it? Did we get something? Oh, yeah, 5, -2, 3. Ha! That's pretty sweet. Love it. Love math. Love math all the time. So it looks like we verified that we did in fact get that. Okay, with your partner, go ahead and do that second one then. Remember, this was the one that had a fraction, 3/2. All right, this is the one that had a fraction. I'll go ahead and pause it while you guys generate that. All right, so what did we get when we did a matrix equation? A matrix equation for that last 3 variable system, for that last 3 by 3. What did you get for your coordinates of the solution triple? Maya?
-2, 4, 1.5.
Raise your hand if you got -2, 4, and 1.5. Yes, and that's what we got algebraically. You guys are awesome. Great work today. So, I don't know about you, but I like using the matrix editor in order to solve a 3 by 3 system when it's calculator allowed because it's way quicker. Not that we couldn't do it the other way, right? We were able to do it algebraically. It's just it was much easier and more efficient to utilize the graphing calculator technology, and that's what we're about. Technology is useful in that it's a tool that can make our lives more efficient. We want to just make sure we're selecting and appropriately using that technology, right, when it makes sense to. All right, let's go ahead and close it up for the day then. Don't call out. Instead, I'd like a little written response from you and your partner. What must be true for you to be able to add or subtract matrices? When solving a 3 by system algebraically, that is pencil and paper methods, what should your strategy be? Number 3, how do you solve that matrix equation? What is it that you do procedurally to both sides? And lastly, how does one determine the dimensions of the coefficient matrix? Please be ready to share your response. I'm going to give you guys about 2 minutes, and then we'll talk about our closure together. Okay, ladies and gentlemen, let's go ahead and share your closure responses with the class. What must be true for you to be able to add or subtract matrices? What has to be true in order to add or subtract matrices? Kendall?
I have to have the same dimensions.
Good. We have to have the same dimensions in order to add or subtract matrices. Raise your hand if you had the same as Kendall. Same dimensions, same dimensions. Good, thanks. Hands down. When solving a 3 by 3 system algebraically, that's pencil and paper methods. What should your strategy be? So what was our strategy? What do we have to try and do there? Joe?
You need to get rid of one variable, so it's just like an variable system.
Absolutely. So we had to get rid of one variable, and we did that in 2 different ways. So that we were chunked down with a 2 by 2 system. So then we could solve the 2 by 2 system, again, continuing on like Bellwork. Nice job. How do you solve that matrix equation? What is it that we're going to do, right, in our last step to solve the matrix equation? A times matrix X equals matrix B. What do? Megan?
You take A inverse times B.
A inverse times B was our last step. That was how we solved that equation for X. A inverse times B. Nice job. Raise your hand if you get the same thing as Megan. A inverse times B. That's what I'm entering my home screen. Way to go. And lastly, how does one determine the dimensions of the coefficient matrix? So how do we get the dimensions of that coefficient matrix? Aaron?
You take the coefficients of all the variables and put them in a matrix, so the dimensions would be the same, the solutions by variables.
Yeah, absolutely. The dimensions would be, right, the number of variables that you have and the number of equations that you have, because you put in the coefficients from each of the variables. So x, y, z resulted in 1, 2, 3. So the number of variables, or I guess number of equations by number of variables. Perfect. it turns out that this always must be square. In fact, we can only find the inverse matrix for a square matrix, but that makes sense because you need 3 distinct equations in order to solve for 3 different variables. So these are always 3 by 3 or 4 by 4 or even 2 by 2. Nice job, you guys. So you notice that you've got several different handouts today. So what can systems do for you? Well, the real power of systems is when those variables x, y, or even x, y, and z represent real-life quantities. And so you've got a multiple assignment today. We've got solving systems non-calculator, which looks just like, right, half of your quiz. It's 2-sided out of 14. Everybody find it. It's got the graphs on there. It's got elimination method and substitution method. So that's solving systems non-calculator. That's 2-sided. Then you've got problem solving with systems out of 4, where I want you to choose the best method and then use the calculator if you want to, or non-calculator, depending upon what it looks like. That is the problem solving word problems, right, out of 4. And then lastly, together, these are great review for your quiz. You're going to read 5.1 and prepare for your quiz. Don't neglect to look over your note sheets too, right? But this is a good review assignment as we build up to our quiz. When's our quiz?
Next class.
Next class. Awesome. I'll go ahead and stop the recording and post it to Moodle. Great work today, you guys.